Good morning. Okay, so I'm here to talk to you about Strace. The idea of Strace, it's a kind of tool that you can use to monitor the conversation that's going on between a user space application and the kernel. It lets you watch all the system calls that a process is making when you're communicating with the Linux kernel. Underneath, it's implemented using a system call called ptrace, and the point is it's a kind of debugging tool that you can use to monitor the complete conversation that happens between the application and user space, all the system calls that are being made. And obviously you can answer questions like, what sort of system calls is the application making? What files is the application touching? What are the arguments being passed to each system call? Did the system call succeed or not? And if it failed, why did it fail? I just mentioned in passing there's a loosely related command called ltrace. And ltrace is about tracing calls through shared libraries. And so it's an analogous tool that you can use to watch what's going on with the shared libraries that your application is using. I'm not going to talk about it at all. I just mention it because it's a related tool. It actually has quite a similar interface, and you might also find that useful to learn about. Okay. The beauty of Strace is it gives you everything in symbolic form. Okay, you get system calls being displayed to you by name. When there are signals involved, you see the names of the signals, not signal numbers. When strings are being used as arguments, you see the strings being printed out, by default up to a certain limit, 32 bytes, but you can ask to get more of each string being displayed. Things like bit masks. For certain system calls, those bit masks are displayed symbolically. In other words, Strace has built-in logic where it understands each different system call and what the flags arguments of those system calls mean, and it has the bits decoded into symbolic form for every different system call. When it displays structures to you, it displays the structures in a nice sort of C format. Braces, and each field is shown with its name. By default, and when system calls fail and you get an error in the global erno variable, you see the name of that error in symbolic form, and you see the textual description of that error. And by default, large arguments and structures are abbreviated by default, but you can ask for the full format of those structures, the full display of those structures. So here's an example of the kind of output you might see when using that expanded output from Strace, where we've got a call to a system call here called fstat. Fstat takes two arguments. One of the arguments is a file descriptor, which is just an integer. But the other argument is a structure that's returned by the system call. And what we see here is an opening brace for the structure, a closing brace for the structure, and then each one of the fields is displayed to us in labeled with its value. And all of the fields that should be displayed symbolically are displayed symbolically. So to take one example, here's a timestamp field, and the timestamp field gets shown to us as a date and a time. Taking another example here, this stmode field, the stmode field gives us two pieces of information about the file. It's permissions mode and also the file type. Now the permissions mode here is displayed in octal because most people understand octal permissions masks on Unix, Linux systems. But the file type is shown to us using the standard constant used in the header files for this particular file type. So it's not displayed to us numerically. Instead, we see sifreg. This is a regular file. Another example, the first field here, stdev, this is telling us what device this file lives on. Okay, fstat is giving us information back about a file. This is the device that this file lives on. Now, devices on Unix, Linux systems are identified by a combination of a major and a minor ID. The major ID tells us what kind of device it is. The minor ID says which particular instance of the device it is. And there's a standard macro in the header files called makeDev that takes those two numbers, combines them to make a bigger number. And that macro is used to display to us the device ID. Okay. Another example here, we've got open. Open takes a path name and a flags argument. Again, the flags argument is displayed symbolically. Open returns to us a file descriptor, assuming it succeeds, and we see the file descriptor number being displayed there. It's file descriptor number 3. So let's take a very simple C program. All it does is write out a string and terminate, and then we'll run strace on that program. By default, strace sends its output to standard error, but we can ask it to send the output to a file instead. So here I'm saying send the output to a log file. I run the program produces some output, and there's a little step I need to mention along the way. We'll look at that log file in just a moment. On some Linux systems, there's a security module that's installed which by default disables the use of the ptrace system call, except in limited cases. So if you find that you try and strace something on your system and it doesn't work, what you might need to do is check, do you have this file on your system, and does it have the value 0 inside? And if it doesn't, then you need to put 0 in that file, and then you can use strace. Otherwise, as an unprivileged user, you can't use strace. Okay, so when we look inside that file, we see a whole bunch of output. So I've edited the output here quite a bit. There was actually about 25 lines or so in this particular case. A lot of those lines were to do with loading of shared libraries that happened at the start of the execution of the program. We'll see lines like this where a certain file is being opened. In this case, it's the cache file being used by the dynamic linker, and mmap calls are being, the mmap call here is probably to do, I was going to say it's to do with mapping some shared library, but maybe the cache library, the cache file is being mapped in as well. But what we see down towards the end is information about the system calls that were actually in our C code. So there's a whole lot of calls that happen at the start to do with C runtime startup, dynamic linking and so on. But then towards the end, we see the system calls that we actually explicitly made in our program. And here's the write call. It had, we wrote onto file descriptor 1, standard output, a string, a certain length. The return value of write was 12. Write tells us how many bytes it's written. Then we see something that's a little bit surprising, because going back here, this was a call to the exit library function. Now, if you know how Unix systems work, you know that the exit library function calls an underlying system call called _exit. And so that's what you might expect to see in the strace log. Instead, we're seeing a call to something else, exit group. Now, I'm going to jump forward there a little bit. If you go and look in the manual pages closely enough, you'll find a lot of annotations these days that look like this: C library kernel differences. And you go and read through and you see, in glibc, since version 2.3, the _exit API is actually a wrapper function in the C library that instead calls exit group. So sometimes you have to do a bit of detective work to understand what you're seeing in the strace outputs. Okay. So I don't know, I've sort of covered a lot of this already, but the point is, again, in the symbolic output, we're seeing the names of system calls, we're seeing the values passed in as arguments, we're seeing for each system call a return value. Some system calls don't return a value, so exit group, for instance, doesn't return, so we see a question mark there. And in the case of system calls that fail, like this access system call here, we see the return value is -1. ENOENT is the symbolic value or the symbolic name of the value that appears in the earno variable, telling us what kind of error this was. And in this case, it's telling us no entry in the file system. This path name doesn't exist. And also on the next line, we see the standard textual description of that error. No such file or directory. Okay. Now, by default, when we use strace, if we try and trace a program, what we'll see is the system calls that are made by the process that executes that program. If that process or if that program creates child processes, by default, we don't see the trace output for those child processes. But we can ask to do so. We can say strace-f, and then we see not only the program that we wanted that we started getting traced, but also the child processes that it creates. Now every line of output in the strace output is prefixed by a PID. This even works with programs that use threads, by the way, POSIX threads, for example. In this case, each line gets prefixed by the kernel thread ID that is used underneath to implement the POSIX thread. And so, again, a little example here. I've got a program that creates a child process using fork. Fork returns 0 when the child returns, and the child prints out a message, and maybe if it was a command line argument, the child will try and exec a command. I'm not actually going to try and do that in the demonstration that we'll see in just a moment. The parent, meanwhile, waits for the child to terminate. And I run the program here, no argument, so it doesn't try and exec any other program. So there's going to be a fork to create a child process. The child process is going to print a message and then terminate. Meanwhile, the parent is going to wait for the child to terminate, and then the parent terminates as well. Helpfully, my program, the two processes print out their PIDs, so we can match that up in the strace log. So when we do that, now what we see is every line begins with a PID telling us which process is producing the trace output, and so we can see which of the parent and the child. The parent was 1939, the child was 1940. Which parent or which process is producing the trace output? What we're seeing very first there, the exec-ve call that was used to actually launch the program. Now, further down, there's a call here to clone. And again, this is where you need to do a bit of detective work, because we had a program that called fork to create a child process, but there's actually no call to fork here. And that's because these days, I don't know if I've got it on a slide, I haven't, but these days, fork is actually a wrapper function in the C library that instead calls the clone system call. Clone provides a sort of superset of the functionality of fork. And so what we thought was a fork system call actually underneath is really a clone system call. So that was a clone system call being made by the parent, and then you can see the parent is calling wait to wait for the child. Again, we see here there's a call to wait for. We called something named wait, but actually this is a wrapper function again that underneath calls a system call called wait for. Again, you'll find all these details in these little pieces in the man pages about the differences between C library and kernel interfaces. So, an interesting thing happens just here. We call wait for. We've asked, the -1 here says wait for any child, and the wait for call blocked. It hasn't finished yet. strace works this out, and it displays to us that this call is not yet finished. Now, here's the child. The child writes a string, okay, a write system call. The printf underneath was using a write system call. And then the child terminates by calling the exit library function, and by now we know that underneath the system call that is being used is exit group. Now, at that point the child process terminates. strace notices that, And so we see that strace tells us that process terminated with exit status 0. And at this point, the parent wakes up again because now it gets informed that the child process is now terminated and the wait for call now unblocks. And we see the rest of the arguments that are being returned by the wait for call. And wait for as well, its return value is the PID of the child whose status is being reported. What also happens for the parent in this scenario is it gets a signal to tell it that the child process terminated. And strace also can tell us about signals that are flying around inside our application. And the signal that's involved here is sigchild, okay, the death of a child process. And signals on Linux systems and on a lot of other Unix implementations as well can be accompanied with a bunch of other data that tells us about the origin of the signal. And so we see things like the information here, SI code, CLD exited. This is telling us that the cause of the generation of the signal was child termination. And we even see the PID of the child that terminated, the user ID of that process, some other information as well. Then the parent terminates and strace sees that. Okay, so if you use strace to look at any interesting program, what you find is any interesting program makes thousands of system calls, tens of thousands of system calls. So you get this enormous quantity of output. And so one of the things you then want to do is say, I want less output. You want to filter the output that you're getting. And there's a few different kinds of filtering that you can do. First of all, there's an strace-e option, which allows you, which among other things can be used to select the system calls that you want to trace. So maybe you only want to trace certain system calls that your application is making. Then you can say strace-e trace equals, and then names of system calls one by one, separated by commas. So here we're saying run the program ls and just trace the open and close system calls, opening and closing files. Sometimes, conversely, you have applications that make a lot of system calls, but they make a lot of the same system calls, and you actually don't want to know about those system calls. A classic example is there are some applications out there that do things like calling get time of day thousands of times a second. Get time of day just returns the current time. Kind of strange thing to do, but some applications want to do it. And maybe you don't want to see all those calls to get time of day in your strace output because they're cluttering up the output and they're not terribly interesting information for you. So then what you can say is strace-e trace equals shriek, as in not, system call, comma, system call, comma, system call. One thing you've got to watch out for here, that shriek carrier, that exclamation mark, is often many shells interpret that character with a special meaning. So quite probably you want to put this piece in single quotes. I don't know, more recently, someone had the bright idea that in strace you could say strace-e equals trace/regular expression. So you can actually write a regular expression to select your system calls. It seems kind of excessive to me. There's only a few hundred system calls, and I don't know if I really want to write regular expressions to select system calls. It seems more than I need. Anyway, it's a feature that was recently added. One other feature that is sometimes useful, instead of specifying individual system calls, you can say strace-e trace and then a system call category. And there are a number of predefined categories that you can choose. strace-e trace equals %file. Show me all the system calls that take a file name as an argument. Or show me all the system calls that use file descriptors. Or the system calls that do sort of process management tasks, things like process creation with fork or clone, process termination, exit group, execute a new program, wait for child processes. Or network-related system calls, all the stuff to do with the sockets API, socket, bind, listen, and so on. And signal-related system calls, memory-related system calls. There's a few other categories as well. Sometimes this is a convenient shorthand, of course, rather than listing a bunch of system calls individually yourself. One of the other things you can do is you can say, maybe there's a lot of signals flying about as your application executes, and you don't want to see all of the signals in the trace output. Again, you can use this -e filter option to select which signals are being displayed. And you can say strace-e signal equals, and then a set of signals. And the set of signals is just listed by name. Optionally, the names of the signals can include the sig prefix, but they don't have to. And so here we're saying, I want to trace the SIG-IO and SIG-INT signals that happen during the execution of this application. And again, there's a not functionality, because maybe there's a certain signal that happens a lot, and you don't want to see the output to do with that signal. So you can say strace-e signal equals not set. One other thing that you can do in terms of filtering is filtering by path name. You want to find out if your application is touching a certain path name and when, and with what system calls. So you can say strace-p path name, and you'll see all the system calls that relate to that path name. And there's some cleverness that goes on here. So first of all, here I'm saying strace-p lib64 libc.so.6. Ideas about which one that is? What file that is? It's the C library. Okay, and I'm just saying for ls, send the actual output of ls to /dev/null so we don't actually see it. One of the things that strace works out along the way is that actually this thing's a symbolic link that points to another file. And so it tells us what the actual file is that the symbolic link resolves to. And then we go and look in the logged output, and we see here a call to open that opened that path name, certain flags, and we got back a certain file descriptor. Now strace gets a bit clever here. It says, that file was opened on that file descriptor. Everything that happens with that file descriptor now, I better tell the user about it, because the user is interested in what happens to that file. And so now there's a whole bunch of system calls later on that all use file descriptor number 3. Okay, we're reading from that file that we opened. We're doing an fstat on that file that we opened. We're doing an mmap from that file that we opened, and so on and so on. And eventually the file gets closed. The file descriptor gets closed. And at that point, strace, of course, works out that, hey, this file descriptor is no longer interesting, and even if it's reused later on with another open on a different file, of course, it doesn't show us the system calls that use that file descriptor. There's a few other sort of related options that you can use in terms of path names. There's an option -y, and when you use the -y option, then when file descriptors are displayed, it also displays extra information about the file descriptor. For example, the path name of the associated file. So this just makes it a bit easier for you to read the strace output. I mean, if you read the strace output, if you didn't use -y and you read the strace output carefully enough, you could always work out what file descriptor 3 refers to, but this is a kind of aid to make understanding the strace output even easier. So here we're seeing file descriptor 3 refers to the path/home/greet and so on. I've made a little mess up editing that slide. That last path name there should say home mtk greet. I tried to shorten my slides, but I failed to edit that piece. Okay. There's also a -YY option. Okay, so strace-y shows you information not just for files, but things like sockets and pipes as well. There's some useful information being displayed there. And for sockets in particular, there's also an option you can use called -YY, which is give me even more information about sockets, and you get various protocol-related information being displayed. So here we're seeing file descriptor 3. It's a TCP socket. There's an IP address associated with that socket, there's a port number, and there's a peer associated with the socket because this is a stream socket connection. So we see the address, the IP address and the port number of the peer socket as well. One of the features that has been added more recently to strace is system call tampering. It used to be you could just use strace to trace the execution of a process. You can now use strace to interfere with the execution of a program. You can cause certain system calls to change their behavior in various ways. And this feature in general is called system call tampering. There's a bunch of different things you can do. You can add a delay before or after a system call. You can say when a certain system call is made, generate a signal. You can bypass the execution of a system call so that when that system call is attempted, the system call doesn't actually get executed. And there's various possibilities that you can do there. You can either bypass the system call and make it look like it succeeded, so it returns a success. It looks like it returns a success status. Or you can make things look like the system call failed with a certain error number. There's even, when it comes to doing this sort of tampering, there's even a sort of limited facility to say which instance of this system call should be tampered with. Just want to check my time. Okay. Now, the way that you use this tampering option, you say strace-e inject, and then you list a set of system calls, and then some option, that says which one of these things do you want to do to that system call. And there's various possibilities. These are syntaxes that just correspond to those options. You can say, I want to make that system call fail with a certain error number in Erno. Or I want to make it I want to bypass the system call and make it look like it returned a certain return value so that it looks like the system call succeeded somehow, returning a certain value. These two options, just by the by, are mutually exclusive. You can't make a system call succeed and fail. Okay, tell the system call, deliver a signal when that system call is attempted, or when the system call is attempted, have a delay before the system call is actually executed or a delay after the system call is executed, or both. So when a certain system call happens, you can have things slow right down so that perhaps while the delay is happening, you can be an arbitrarily long delay, then you might do some inspection of the rest of the environment that the process is running in, because you want to see how do things look just at the moment that the process makes that system call. And then, as I said, there's a sort of limited facility to choose which system call you want to interfere with. And you can say : when, and then some sort of expression. So for instance, when equals n says tamper with the nth invocation of a certain system call. Or tamper with all the invocations starting at the nth call and everyone there afterwards. Or starting at nth and then every s step, every instance of an invocation to that system call. Okay.
And that's the only way. So I mean, like open, you will have maybe 3 or 4 opens even before your program starts. You would just need to run them and count them. And
I said it's a very limited form of choosing. I'm sure many people would like what you like, but that doesn't exist yet in strace.
But it's probably a good start, maybe.
It's a start, and this feature was only added, sort of less than 2 years ago. For a long time, the development of Strace was fairly sedate. But in the last 2 or 3 years, there's been a whole lot of development work going on, a whole lot of new features being added. So who knows? Maybe you'll get what you want in the not too distant future. Okay, so here's an example then where I'm saying strace -y, Y to get extra information about file descriptors, trace the close calls. Okay, this is a shorthand here, by the way. I've said -e close. I could have said -e trace equals close, but you can actually do it shorter in some cases. And then -e inject for the close calls, make them fail with the erno value 22, but only make the third close call fail. And so we see here that the program is making a series of close calls. The first 2 close calls succeeded. Okay, and the program we're running, of course, over here is ls. We see the first 2 close calls do something, but then the third close call looks like it fails with an error, e-inval, and we see the corresponding error text for e-inval, and we also get an indication from strace. Actually, this was an injected error. Now, after this, because ls tried to use a certain file and the open failed, after this, ls got kind of sad, and things started to go bad. Okay, so ls eventually decided, I can't go any further.
Sorry.
Yes.
You said error equals 22.
Yep.
What does that mean?
Oh, sorry. Yes, it's a good. Oh, sorry. I do have it here. Yes, I do have it here. But 22 is the numeric value of the e-inval error.
Okay.
Unfortunately, you have to specify the numbers numerically, at least as far as I know. So there is, by the way, a little program around nowadays. It's a quite useful little program that is not so well known, and I just show it to you. It's a program called Erno. Now, it might not be installed by default on your system, but there's a package called moreutils that is available for most distributions, and it gives you this little tool. And it's really useful because I can say Erno22, e-inval, or I can say Erno e-inval, go the reverse direction. This is quite useful as well when you're using the manual pages, because in the manual pages the errors are listed symbolically, but the errors are actually numbers, and sometimes you actually just see numbers being output from programs. And you want to say, well, I know I've got a certain error number, and I can see there are error names in the manual pages. What does that number mean? You could go and look in the header files. That's kind of painful though. This program gives you an easy way of doing it. Okay.
Then it says -1.
-1. So when a system call fails, what's happening is it has a return status, which is typically 0 on success or -1 on failure. Some system calls return some sort of positive value on failure, on success as well. But the point is -1 is return on failure, and then there's an additional channel for giving you further information about the error, which is the Erno global variable. And the e-inval value is what's landing in the Erno global variable. And Erno is a special variable dedicated to the purpose of error reporting, and strace knows this. So it's telling you what, when strace sees, oh, -1 return, oh, that means there's going to be something useful in Erno, and it shows you the value of Erno. Okay, I just very briefly mentioned then, there are a number of other options that are potentially useful from time to time. strace-c, this says give me a summary of the system calls that my program made. And what you see here is the number of system calls that were made to alarm. This is a system call called alarm. And you can see for each system call, if there were system call instances that failed, you can see the number of system call invocations that failed. What you also get is some timing estimates where you see there's an estimate here in seconds of how long it took to make that system call. I would totally take this with a grain of salt, because the way strace works, it uses the ptrace system call, and the way ptrace works when it's monitoring another process is it stops that process every time it makes a system call, just before it makes the system call, and just after the system call returns, for every system call. So just by the way, strace can slow a program down quite significantly because of all of these stops and starts. I can't remember if I've got a slide here about it, but one of the things you want to be, you can use strace to trace a live process in production. You can say strace-p, maybe oh yes, I have it here on the next slide. strace-p to trace a running process with a specified PID. And then you start seeing live tracing of that process. You can even use that lowercase p option multiple times to trace several processes at once. When you don't want to trace anymore, you type Control-C, that stops the tracing. Generally, you can only trace the processes you own unless you're a privileged user. When you do this, you can really heavily impact the performance of your application, because every system call results in 2 stop-starts. So 2 orders of magnitude slowdown in system calls is probably what you can expect. So think twice before you do it in a production environment. If you use strace-p-f, then you can trace all the threads in a multi-threaded process. Okay. There's a few other options as well, which I'll just mention very briefly. -v says be verbose, don't abbreviate structures and arguments that are shown to us, because by default, strace, if you've got a very large structure, it only displays to you part of the structure, but perhaps you want to see all the structure, you can use -v. By default, strings, when they're displayed, are limited to 32 bytes of the first 32 bytes of the string. Again, you can change this as an option, strace-s and then string size. Just by the way, path names, strace knows that path names are special. Regardless of this option, it always displays the complete path name string when it's displaying to you information from a system call. There's various options to show you the start time and duration of system calls. Again, I would treat this with a bit of skepticism because of the way strace works, but they can give you a flavor of where your program is spending time in its system calls. So -t and -tt are options that you can use to add the wall clock time, so you see what time the system call was made. -tt includes the microseconds as well. -T, how much time was spent in each system call. One other option that is occasionally useful, strace-i, show the value of the instruction pointer at the point where the system call was made, so you can see which part of the code was making that particular system call. And I'm done. Okay, just in time. There's even time for 1 or 2 questions. Yes?
So you can trace all threads in your program?
Yes.
Trace a single thread?
Can you also trace a single thread?
I know the thread ID or the...
Yes, I think you can do that just by specifying just the thread ID. I've actually never tried that. I've always wanted to trace either the main thread or all the threads, but I'd be reasonably sure that you can just say strace-p and then the thread ID itself. We could answer that question very, very quickly afterwards. Okay. Other questions?
Yeah,
Yes.
about error injection that you have shown, is there any clever way to use this to do testing on your program? How do your program react?
I think that's the intention. You could do this, but I think in the what I think it's interesting that they've added this. It's not clear to me what the real use case is, because there are other ways to do this better. Okay, in particular, you can do things like LD preload techniques with shared libraries, where you intercept calls to system calls and have the preload wrapper make it look like the system call succeeded or failed, or even just does something else completely. Or you can use seccomp. And seccomp is a technique for preventing an application making certain system calls. And one of the options you've got is say, make that system call look like it failed. I'm going to talk about seccomp actually tomorrow. So yeah, it's there as a feature, but it's not the tool I would reach for first. I would be looking at the other tools first, just because they offer more flexibility. But maybe the intention is with Strace to add, build on this functionality so that maybe you can do more powerful things in the future. Patricia?
You could maybe use it for black box testing. Like you say, like you want to see if this application survives a certain thing failing, like opening a file or something.
Sure, but I would think about, again, seccomp probably for doing my black box testing. In that case, having a seccomp wrapper that sort of then loads the program that I want to black box test. Just because, well, I don't know, I like seccomp. It's fun, but it is also much more powerful in terms of what you can do. It is, I guess, the one thing I would say in the favor of the inject technique for Strace is it is really simple. It's easy to do. Okay, doing seccomp takes some effort. Doing LD preload takes some effort. So perhaps if you want to just do a quick test, what happens if I make that system call fail now? What does my application do? So it could be a quick first shot at seeing, I do that black box testing, the system call fails. What did my application? Did it gracefully handle the error? But if I want to do more sophisticated testing in terms of black box testing, failure mode testing, I would be thinking about the other tools. Okay. Knut.
Will Strace allow you to instrument a syscall to return an error no value which is not possible according to the POSIX standard? I'm not sure.
So can you instrument a system call value to make it return a value that wasn't?
That should never happen.
That should never happen. Sure, it's just a number.
Yeah, because it doesn't really have a look.
Yeah, no, there's no limitation on the error value that you could, well. Practically speaking, there's no limitation. There is actually a limitation to do with the way system call. Well, actually, no, I bet that's not really a limitation in this case. System call error numbers on the Linux kernel or the glibc expects them, or the C libraries expect them to be in the range 1 to 4095, and they have certain rules around interpreting the return values of system calls that are based on that assumption. Now, the actual error numbers, are 1 up to a few hundred, so we're nowhere near that limit of 4095. But I suppose when you're doing injection with Strace, yeah, you could put any old value in error. It could be above 4095 because this is a level sort of a.
So you can create a situation that could never occur.
Yes.
Yes, it could, because programmers might do that. By explicitly saying no.
Right into a random.
Yeah. But yeah, they're just numbers. Yes.
How does Strace handle context switching if you have several threads?
How does Strace handle context switching? Well, underneath, I don't know the details really, but I mean underneath what's going on here is a certain system call called ptrace, and ptrace is just being used to monitor the process. And the way that ptrace works is an interface into the kernel, and the kernel informs the user of ptrace every time something happens with that process that is system call related. So it's all being, the kernel knows that a certain process is being traced. It knows the identity of the tracing process. And so when some trace relevant event happens, it just causes the ptrace call in the tracing process to get informed. Is that a question also? No, just stretching. Okay. Alrighty, thank you very much.